The Vernier motion encoder system allows you and your students to measure the position of a cart as a function of time easily and with very high accuracy. It's used a bit like an ultrasonic motion detector, but doesn't have the accompanying frustrations of detection of stray objects and other kinds of interference in the classroom. For example, if I had a motion detector at this end of the track and a computer screen here, the motion detector would be blind to the cart's motion on most of the track. The motion encoder system consists of three new pieces. First, the track has a bar pattern printed on it. That bar pattern has a 4 millimeter period, allowing you to measure the position of a cart to the nearest millimeter. The cart has a sensor on the underside. The sensor detects the passage of the bars on the track. That information is sent by an infrared beam to the receiver. The receiver is plugged into an interface. In this case, I'm using a LabQuest Mini, but you could also use a LabQuest 2 or a LabPro or even an original LabQuest. The interface is plugged into a computer, and I'm going to use Logger Pro to graph the motion today. I'm going to move the cart up to the top and launch the software. That's establishing my 0 position. And if I let the cart roll down, you can see on my computer screen the current position is being shown in this digital readout. Let me start data collection and give the cart a push, and it rolls up and comes back down the track, moving with constant acceleration. If I take a look at my position data, I get a very nice, clean parabola. There are no spikes. There's no extraneous stuff that you've got to explain away to students. The velocity graph is showing a nice linear portion corresponding to when the cart was freely rolling. I can do some analysis here. Let me select a region of the graph, and I'm going to choose to do a quadratic fit here. And indeed, my fit is quite good, and you see that the position data follow that expected parabolic form. I could go to the velocity graph, select the constant acceleration portion, and request a linear fit. And indeed, you can see that the fit is quite good and gives me a good measure of the value of the acceleration. Now, one of the things that's hard to do with a motion detector is to get high-quality acceleration graphs. Often they're a bit noisy, too noisy to use with students. Let's take a look at what the acceleration graph looks like for the motion encoder system. I'm just going to click on the y-axis label, and I'll get an acceleration graph. And you see that the part of the graph corresponding to the free-rolling part, motion of the cart is approximately constant. I can actually go one step beyond the acceleration graph, which is the second derivative of position. Let's take a look at the graph of jerk as a function of time. Jerk is the third derivative of position. Such a graph is essentially never used with a motion detector because they're too noisy. But let me draw that graph and see what it looks like. Since the acceleration graph is constant, the jerk graph should be 0 during this time interval, and indeed it is. That would be tough to do with a motion detector. The motion encoder system can be purchased as a complete unit with 2 carts, a track, the receiver, and other hardware. You can also buy pieces to upgrade an existing Vernier dynamic system to become a motion encoder system. If you like, you can add a second receiver and cart to a motion encoder system and monitor the position of 2 carts, allowing you to do collision experiments and do conservation of momentum, conservation of energy experiments. So that's the Vernier motion encoder system. If you'd like more information on that, check out our website.